We first begin with our first example about how to use correlation procedure in the SAS Studio. So we first input our data set with four variables. The first variable is a character value variable, which is name, to indicate the name of a person in the class, followed by three numerical variables, which is height, weight, and age for that person. So before we move on to how to calculate the correlation, first we would like to take a general log about how these variables behave. So we use the plot procedure to produce the pairwise scatter plot among each pair of the numerical variables. So let's run this chunk of code. It's easy to see that for each pair of the three numerical variables, they are somehow linearly distributed, indicating a very big positive correlation coefficient for each pair of them. Now we move on to the correlation procedure step. We first specify the name of the data set using the data statement, and we use the var statement to specify the name of the variables whose correlation coefficients we are about to calculate. Now let's run this chunk of code, and we begin to read the table. The first table is about the basic descriptive statistics of the three variables, and the second table is the correlation table. Apart from the correlation coefficients, it also shows a p-value for each correlations, which is an indicator for the hypothesis testing problem, whose null hypothesis is the correlation being zero. Now we move on to and we took a closer look of the table. We could find that for each correlation, the p-value is very small, indicating that for each pair of the variables, they are highly correlated. Now we would like to move on to how to produce a regression model in SAS, where we will use the regression procedure to we first specify the name of the data set using the data statement. Here we would like to still use the previous data set, and we use the model statement to specify the model. On the left-hand side is the dependent variables. Here we will use weight, and on the right-hand side are the independent variables. Where we will use only one variable, the height. And if we would like to output the results, we will also use the output statement with several options. The first option is out here to specify the name of the output data set, and we use the R options to show the residuals and the P options to show the predicted values. Now let's run the model here. Now let's begin with the basic uh, tables. In the first table, we have the ANOVA table to specify the F value and the P value of the model, as well as the sum of squares and and the degree of freedoms. And the second table outputs some basic measures of our regression model, which include MSE, R-square, adjusted R-square, and several others. And the final table is about the estimated parameters, where we have to obtain the value for the intercept of the regression model, as well as the coefficients for each of the independent variables, where we could also obtain the t-value and the p-values to check for the significance for intercept and all other independent variables. Here are several diagnostic tables for the model, several residual plots and leverage plots. And as well as we have the predict values plot with the confidence intervals. And we also have our final table, which includes all our data set, the predict values of the regression model, as well as the residuals. Now we like to do a basic model checks for our regression model. We first use the plot procedure step to plot the residual plot, where we would like to produce the scatter plot of residuals against the predicted values. And we also like to do the normative check for the model, where we will use the universal procedure step and with normal options and the data statement to specify the output data set. And we choose a variable to analyze as the residuals, and we'll also produce a probability plot for the residuals. Now let's run this chunk of code. The first plot is the residuals against the predict values, and we can see like the residuals are somehow very equally distributed in this plot, indicating our model might be a correct choice. Then we move on to the output of the universal procedures. It first outputs some basic statistics, also have some test for the mean of the dependent variables, and we also like to see the test from normative results, which we could see from this basic quantile plot. In the plot, we could find out that the residuals for the model are almost distributed in a straight line, indicating that um, the normality assumption is satisfied for our model. Now we move on to our final example about using GLM procedures. We would like to input our data set, which have three original variables: the diameter, the height, and the volume for a tree. And we also create three new variables for the data set, with the first one, x1, is a logarithm of the diameter, and x2 is a categorical variables which categorize the trees into three different classes according to the height. And the final new variable is y, which takes the logarithm of the volume. So here we would like to produce a model which could predict the log of the volume of the tree based on the tree's diameter as well as its height, as well as its class of the height. Uh, Again, we use a GML procedure. We would like to see how these three variables behave from a scatter plot. So we use the plot procedure to plot our independent variable against our two dependent variables. Now let's run this chunk of code. We could see from our two plots. The first plot is our dependent variables y against our numerical independent variables x1. We can see somehow it was very linearly distributed. And we also plot our dependent variable against our categorical independent variables. We can see some similarities between those three classes of trees. Now we will move on to our GML procedures. We first specify the name of the procedures and use the data statement to specify the name of the data set, which is the tree data set we have just inputted. And we use the class statement to specify the categorical variables and use the model statement to specify the model. On the left-hand side is still the dependent variables as the regression procedures, and we specify the independent variables, both numerical and categorical on the right-hand side, and we use the output statement as before um, to output the result, and use the out statement for the output data set, R for the residuals, and P for the predict values. And we can also use the min statement to choose the variables whose effects we would like to evaluate. Now let's run the GLM procedures for our model. The zero GLM procedure first will produce some basic information about our categorical variables, and it also do a ANOVA test for the whole model, which gives out the F value as well as the P value for the whole model, and some basic measure statistics, squares or MSE or something else. And we would like to see the F values for our first category and F values for our second category, and the basic analysis covariance plot for our dependent variables, and the distribution plot for our dependent variables, and also some basic evaluations from the model. Now, if we like to do model checkings for the GML procedure, it is much similar, which is much similar as the regression procedure. We first use the plot procedures to plot the residuals against our independent variables and our predicted values. And we also use the universal procedures to analyze our residuals as before. So let's run this chunk of code. Then we can first see the three residual plots. The first one is the residuals against our numerical variable. The second one is the residuals against our categorical variable. And the third one is the residuals against our predicted values. Since the residuals are somehow equally distributed for three of the graphs, we could say that our model is correctly specified. The univariate procedure produce some basic descriptive statistics for the residuals, and test for whether the residuals is distributed around zero, and we could see it has a very big p-value because we could make the conclusion that the residuals are somehow distributed around zero. And now we do our probability graph here as the box plot, the quantile plot of the residuals against the normal quantiles. Although it is somehow a little bit tilted, the residuals are still distributed along the straight line, where we can make the conclusions that the normality assumptions of the model is correct.